Okay, good afternoon. We will now have a panel discussion on science and technology. And I first introduce the panelist in front of you. From right in my side is Dr. MIYOSHI, Program Director of Moon Shot 8, and Professor Park, Dr. Tessendorf, and 4 researchers on behalf of Core Research Project, Dr. SAWADA, Dr. FUDEYASU, Dr. YOROZU, and Dr. YASUNAGA. Okay, I would like to proceed the discussion as a moderator, Tetsuo NAKAZAWA. And we have 70 minutes for panel discussions, and we have 7 panelists, so that means individual people may speak only 10 minutes, if average sense. And I prepared several questions to the panelists, and I'm not sure which question I start with, but maybe I start from the easier one. And as you may know, 2 years have passed since the program started. And yesterday and today, we had lots of accomplishment in the core and feasibility studies, both. And they showed their interesting result. But now again, I will ask all project managers to say a little bit few words, what is the most appealing result so far you got in your project? Maybe it's a simpler one, right? So maybe Sawada-san, do you say a few words?
Is it really easy one? Okay, so what we are challenging is to change the game. So I think the most of the work try to prepare some intervention methods and then evaluate how that intervention methods affect to your control objective. I call it that's a forward approach. And we would like to have the backward approach as well as a forward approach, which means that we first set the objective and try to calculate the backward from the macro scale to the smaller scale to get the optimized perturbation or idealize the perturbation. So we are now trying to developing such kind of the methodological the tools to realize the backward approach. Of course, the forward approach is always important, but by combining the forward and the backward, we can change the game of the weather control problem. So that's kind of, we believe that's kind of a unique point of our approach. And it might be the appealing point, I think. Thank you.
Okay, thank you. Jeff-san?
Yes. So, so we are trying to reduce the typhoon intensity by human intervention. And so we have conducted many methods. And so I personally, I believe the cloud seeding, as I presented yesterday, is a little bit promising. So it seems, but the mechanism for reducing typhoon intensity is still not fully understood. But we can see the, so seeding within the IO suppress the intensity, but oppositely, so seeding in the outer rain band enhance intensify the typhoon intensity. So that's a very interesting. But so we have so we didn't have any idea about the mechanism, but it's being increasing considered. So in terms of the mobility, so I think actually aircraft played a significant role. That's it.
Okay, thank you. YOROZU-san, please.
Okay. Okay, thank you. Before answering the question, I'd like to make my self-introduction. I'm Kazuaki YOROZU from Kyoto University. Actually, I belong the project Yamaguchi project. Unfortunately, the project manager, Professor Yamaguchi, cannot attend this time, so I joined instead of him. And regarding the appealing point, shortly speaking, that we can show the possibility of the rainfall controlling by the human intervention. For example, we can assume the wind turbine, and we can reduce the rainfall intensity of the guerrilla type rainfall. Simply speaking, the isolated cell, the amount of the rainfall is 20% cut. And also the linear shaped rain can be reduced by assuming the curtain, offshore curtain, or dryer seedings. So that is our achievement, I guess. So thank you very much.
Okay, Yasunaga-san.
Okay. Sorry, so I have to also introduce myself. So I'm sitting here on behalf of Kotsuki-san. So Kotsuki-san has a class today, so I would like to introduce our research activities here. So appealing point is that so targets of the SAWADA-san's group and the FUDEYASU group is a typhoon, of course. So under Yamaguchi-san's group target is a spontaneous convection. So our target is a precipitation, organized precipitation system, and that is a unique point in this project. And we show that the possibility that we can reduce the water vapor in front of the precipitation system, and we can actually control the organized precipitation. So that's our most important point of our project.
Okay, you finish? Okay. Yeah, thank you for all. And then, Miyoshi-san, you may say a few words.
Okay. International Symposium, but we focus on mathematical aspects. So I forgot the exact title of the symposium last year, but last year was more like on the mathematics around the weather controllability. So as Sawada-san said, so we have some tools or methods to perturb the atmosphere, and we would like to see what kind of perturbations can create what kind of change in the weather. But it's not, I don't think that's a control. So we would like to apply the optimal control theory to the weather system. So the weather system, so in the phase space, we can have the orbit of the weather state, the atmospheric state. And because of the chaotic dynamics, the small perturbations can grow and lead to completely different fields in the future. And the idea of the control is to choose the orbit of this trajectory. So we have some uncertainties, and also we could introduce some perturbations, although it's very limited. But we would like to define what is the preferable future state, and then we try to select the trajectory. But as I said, it's unpredictable because of chaos, but we could push the system in a very limited way. But if we continue doing that, so once we push then the future changes slightly. Then we observe what change is made, and we get the feedback from the observation, and we continue the small change that will lead to the preferable future. So that's the idea of the control. And I don't think that we can control everything. We need to know what kind of phenomena that we can really control. And we have very limited controllability. So that's a problem that we would like to understand. And so far, I have seen, so yesterday, the core projects presented their achievements in the past 2.5 years, less than 2.5 years actually, but a little more than 2 years effort so far. So it's very short time so far, but it's the time to see what has been achieved. And so the last year we had only the mathematics of controllability as a topic of this symposium, but this year we really aim to discuss the controllability. And I have seen that the smaller phenomena may be easier to change, of course, but the bigger phenomena like tropical cyclone, it's much bigger because it has lots of, maybe thousands of individual convections forming the tropical cyclone, single tropical cyclone. So comparing with changing a single convective system, such a big, well-organized convective system like tropical cyclone has much more, the size and scale bigger and more difficult to change. But what we could do by human power is very limited. So we really need to understand what kind of tropical cyclone may be controllable, and we need to understand what controllability we have, and we are, I think, in the middle of finding the controllability of tropical cyclones. But at the same time, particularly Yamaguchi project showed a very promising results yesterday for a single convective cell, and only modifying winds by an equivalent of 2 big wind turbines that sounds feasible can reduce the intensity of the convective rains significantly. So that's a major, I think, major achievement that this program made so far as a whole. And so 2 years ago, we didn't know if human power can really have the controllability of such a weather system. Because if you look at the sky, and if you look at even single convective cell, it's huge comparing with the size of what humans can build. So whenever, I have been doing this role as a program director, but just looking at the weather model results or thinking about the mathematics of the control, so if we just sit in the room, we tend to feel that this problem may be much easier, but once I go out and see the real clouds, what could we possibly do? That's always, I felt, it's almost impossible. But now, Yamaguchi project showed very robust results by changing the inputs at other locations, or those sensitivities showed really robust results of reducing the intensity of precipitation. So I now feel that we are really getting closer, at least for the single convective cell. And the next question is if we can predict the convective cell precisely and decide where and when to put those devices. But now it's a critical stage. For the next 2 years, probably, we hope that we have something more realistic to move on to the real field experiments. Thank you.
So, Miyoshi-san said the maybe heavy precipitation event is a little bit easier by means of size, and maybe we may change the precipitation event, but maybe it's a little bit difficult, more difficult for typhoon case. But still, this is a moonshot program, so then we already know it's really challenging issues, not so easy to solve. So that's why I hope there is still some room for tropical cyclone controllability as well. So maybe I will discuss later on this topic. And we have 2 keynote speakers. You have any suggestions or comments on this? Park-san?
Okay. Yeah, during the last 2 days presentations, I basically learned a lot. And because Korea we are doing some kind of cloud seeding, but just for enhancing precipitations, but not for controlling the weather. So this Moonshot 8 program, weather controllability, is a great step to do something to control the weather. And probably I am a little bit afraid that it could end up with climate control too, if we repeat this kind of weather modification experiment. Anyway, I noticed that you have many interesting ideas to control the storms and bigger sized typhoons. But my suggestion is that doing that kind of experiment, first using numerical model is a good idea to find the right place to intervene and to get desirable result at desired locations. But the atmosphere and atmospheric model, they are highly nonlinear, as Miyoshi-san said. Then probably if we add up something at some point and some location there, we may expect that it could respond in some way like we have desired, but actually it may not work in that way. Yesterday I saw the ensemble approach to pick up one special case that we desire to have. Then probably that might be the best trajectory or best option that we wanted to have. Then the other perturbation runs, we may run the model and then put some control factor there to make this trajectory go into the desired one. But if we do some early application on that control point, for some short time it may follow the desired track, but eventually it may just diverge out. So how can we determine that kind of diverging point, and how can we find that? And then if we find that kind of diverging point, then what kind of other control factor we should keep? That kind of thing would be another very complicated thing and the challenging problems. So many things need to be considered, I think. Okay.
Okay, thank you. Sara-san?
Yeah, I want to pick up on that note that Dr. Park just described about knowing the right location for the intervention and using our models to really study that. To do that, we need our models to be really good, really good. The speaker earlier today that was talking about some of the new modeling development, that was very exciting to see, and that's exactly what this program really needs to do, because until we can really predict what's going to happen in the natural world, it's going to be very hard to modify that in a way that we intend the modification to be. So this type of research that's increasing our understanding of the typhoon processes and intensification, the heavy rainfall, it's all very beneficial to then understand and improve our understanding, and including human impacts, whether they're intentional, like we're studying these modifications with cloud seeding or other interventions, or unintentional, because we do know that humans have an impact on our weather and our climate. That's why we face anthropogenic climate change. So improving that understanding of how human impacts, whether they're intentional or not, are occurring, to then feed back into improving our predictions of the natural system is the fundamental baseline here to build from. The other thing that keeps replaying in my mind as to the challenges here is the scale of intervention. So I think this also goes to your comment earlier that the scale of the typhoon and knowing the size and area that you would need to intervene is a huge challenge. When is that feasible to actually do the intervention at that scale? This is the same kind of challenge that climate intervention, climate geoengineering is having as well, is that they've run the climate models, they know this could happen if we had more stratospheric aerosol, but then how do you actually do it at scale? So that's another important component that will be a continuing challenge. But I think that fundamental understanding and improvement, representing it in our models, will be a huge benefit coming out of this program going forward, because the better we can do there, then we can better understand how we modify it intentionally or not.
Okay, thank you very much. The model improvement is really crucial part in the program, I suppose. And this morning, Dr. Chan also showed the aerosol interaction with tropical cyclones. That's also very new topics for us, and we are working for it. Shima-san is also working super droplet method to get a precise distribution of the not only aerosol but also cloud droplet distributions. So, and how do we proceed? The first 2 years and also another 2 years, one of the target in our program is to simulate the impact of the intervention in the model simulations, and by assuming some sort of engineering tools, engineering devices, like maybe yesterday several people already showed some curtain applications, and also wind turbine applications. So, but to do it, the model representation is accurate or not. That's one of the key issues. So then maybe all 4 core project is working to improve the model as well. And but I would like to know from all 4 PMs, what is your current obstacles in the model development, and which part is we have to overcome in the model development? Do you have any idea? Which is the most important component to improve Okay, Sawada-san.
If I just raise a component, that's a crowd microphysics. Crowd microphysics is evil in the model. And also, I would like to say that it is not so good that you have the uncertainty in the model, but the worst case is that you do not know even the uncertainty exists in the scheme. So to quantify the uncertainty is really important. So even if you have a large uncertainty in the model, but if you quantify that uncertainty, you can deal with it to consider the interventions. Okay, but the uncertainty should be quantified by the observation. So if you do not have any observation evidence, you could not quantify the uncertainty. So that the observation is also really important. We should not just stick to the model, but we should consider the design of the observation network to quantify and reduce the uncertainty in the model. That's the comment, I think. Thank you.
You mean uncertainty includes many different kinds, not only model uncertainties, but initial uncertainties or physics uncertainties.
So we know the uncertainty in our predictions, but we should decompose that uncertainty into the several parts of your prediction system, right? And actually, it is very difficult. And maybe I think operational system cannot do it right now. So, but the point is that, it is ideal that we have the model with no uncertainty, but that's inevitable. But the second best case scenario is just we have the uncertainty, but we exactly knows the uncertainty. That's good to consider about the intervention process. So that's kind of second best solution might be possible within the reasonable time frame, I think, if you have a good observation.
I would like to comment on that. To reduce the uncertainty, we need some sort of for example, observation to verify. But for microphysics, maybe it's really difficult to evaluate and validate the schemes. So if you can do it in 10-meter resolutions or something in globally, maybe impossible, but so reduce the uncertainty is also very difficult in some sense, I suppose. Okay.
I just want to add on that too, because that's exactly what I was thinking about. The observations are a huge limitation. It's not just the ability to validate or quantify the uncertainty in a microphysics scheme, but some of the sources of uncertainty due to our initial conditions are due to the limit observations that we have as well. So yeah, that's a really important one to improve our prediction or improve our observational networks in order to reduce those uncertainties and or be able to quantify those uncertainties.
Yeah, is there any comment on this from other PM? FUDEYASU-san?
So I agree with Sawada-san's comment, and so because we are dealing with a typhoon, so it's hard to observe the typhoon in terms of the cloud physics. But now, so one of my team trying to observe directly by using the aircraft to the. So actually, so now, so he's preparing the observation for the typhoon coming to the, not Japan, but other country, but they are trying to prepare the observation. So, but using the other budget, not this budget. So if we will use a model with great accuracy, so we need to observe more, but it's hard to, I cannot say something, but so I want to request observation term.
Okay, thank you. Any other comments? Okay, so maybe let's change or no? Okay. Oh, Park-san.
Okay. Uncertainty is a big problem, as Sawada-san mentioned. We know that there is uncertainty in any numerical model, but if we know the characteristics of uncertainty almost perfectly, then it will be really good for applying it to weather control problem. But the uncertainty may be attributed to model deficiency, but also attributed to non-linearity of the atmosphere and model itself. The problem is uncertainty itself is also non-linear, and it has a non-linear evolution. So it's very hard to have a perfect knowledge on the uncertainties in these days. But what is good is that our technique on parameterizations had been more sophisticated and had a pretty good advancement. Although we have very limited knowledge on these kind of physical processes, so far we have the best options for physical parameterizations and techniques. So under the given situations, we may choose which one would be the best scheme set or something like going to optimization concept. So we may not find the truth or the really good one, but at least we may find some kind of optimal way to treat the uncertainty and to get better simulation results out of what we have in these days. So we might try in that way continuously.
Okay, thank you. In an ideal case, we have some sort of complete model, and then we simulate maybe 2 or 3 hours forecast to detect the occurrence of a heavy precipitation event in the forecast. And then we prepare some aircraft or whatever to intervene over some extreme convective event. And to do it, after interconvention, so then we also have to check the impact, right? So then at the same time, we can also use a model by putting some AGI or whatever, where the simulation is right or not. So then compared to the real world, then you may say to the public, okay, we could simulate correctly and without intervention, so then we have a very strong tropical rainfall event over there. So then we could reduce the precipitation. So then in that sense, if we have uncertainty in the model, even in 2 or 3 hours forecast, so then maybe I cannot persuade the people to convince the intervention. So in that sense, the model accuracy, of course, is really important, especially for this kind of program. So in that sense, it's a little bit different from other program, I suppose. And we have to convince the people Otherwise, we cannot do it. Any comment for that? Yes.
So, good. So, we never have perfect model or the perfect observations or perfect system. And we always have, well, we try to reduce the errors in the model or the observations, but still we never have the perfect system. For the control system that we develop, we cannot avoid forgetting about uncertainties. So we need to include the uncertainties in the system explicitly so that we consider these uncertainties. So we have uncertain forecast. We have ensemble forecast to consider the uncertainties. And if we run 1,000 ensemble members, what if we had only one ensemble member out of 1,000 showing the extreme rain case? Shall we do something? Well, that kind of thing that we need to include in the system. Because we never have perfect forecast. And if it's too late, then there is limited controllability. If the event is too close, then any actions take time to make the effect. So we need to have some lead time, then the ensemble spread getting larger, but that time is the time that we can do something. So we, of course, need to reduce those ensemble spread or uncertainties, but we cannot avoid having those uncertainties because the system is chaotic, particularly for the heavy rain case. It's more chaotic than the calm weather case. So we have faster error growth in those cases. Then we need to include, even if we improve the model, because of chaos, we have those uncertainties. And I should say that in our feasibility study before this moonshot goal is established, we did the moonshot millennia project. And in that millennia project, we developed a strategy or method to include those uncertainties, to make decisions, what kind of actions to make, and to control, in our case, the Lorentz model. But that was quite successful. So that's the mathematics. So it's a theory, but this theory can be applied to the real system. And depending on the accuracy of the model, we will have different scenarios. That's something that we should investigate. But that's not have been done yet in this program.
Okay, thank you. But I experienced the outlier of the ensemble sometimes shows a real occurrence. So that's really tough. Ensemble me doesn't tell us sometimes, not always, but sometimes.
So in our previous study, we run the ensemble, and once we see, we need to decide how long we run the forecast to make decisions. That's a forecast horizon. And then we have the ensemble spread. And if we have single ensemble member showing over threshold, so some extreme events, to avoid the extreme events, we need to take the action. And many cases that real true state doesn't reach to the extreme, but the ensemble shows the extreme. So those cases, in the real case, we didn't need to take any action in those cases, even though one ensemble member showing an extreme case. Most of the case, it doesn't happen. But because our prediction is uncertain, we need to develop a system that considers those uncertainties, and then we need to compute the cost and benefit to put the threshold where we really need to make the action. The action takes the cost. So that part I didn't work yet. I didn't have enough time. But that's something that we should do in this program. Or I could do separately from this program, but
Okay. I would like to come back the theoretical framework of Miyoshi-san developed with Dr. Sang and chaotic control, and by using very small forcing to produce large changes in the future. But so far, I wonder of course, for heavy precipitation event, there is some possibility to control, but the issue is how large the perturbation or forcing is. So theoretically, chaotic control may work, and how applicable the theory into the real world is still maybe premature stage, I suppose, right? So, but maybe all 4 PMs is working for it, I suppose, and but not easy for typhoon case. Is there any comment for typhoon PMs, FUDEYASU-san, SAWADA-san?
Yeah, I personally, I'm really optimistic about the potential of the approach that Miyoshi-san mentioned. But I want to make it clear that there are both good uncertainty and bad uncertainty. So we have a growth of the initial perturbation due to the chaotic nature of the phenomena. But at the same time, we have an uncertainty. This is a prediction uncertainty. But that uncertainty is actually the source of the controllability. But what the bad uncertainty? Bad uncertainty is a model uncertainty. So you can simulate your growth of the perturbation. But that growth of the perturbation, it themselves might be wrong because you are using the wrong model, right? So that's a bad uncertainty. So we should be clear that uncertainty is not always very bad for the controllability, but there is exactly the bad uncertainty, which is a model uncertainty. So we should reduce, or we should quantify the model uncertainty, and then to leverage the good uncertainty, which is the initial condition uncertainty. So that's what I would like to say. Thank you.
Okay, thank you. Okay.
As Miyoshi-san mentioned about ensemble focusing, generally we assume that ensemble focusing, the benefit is you can get the ensemble mean out of some kind of uncertainty range, right. And you can consider the ensemble mean is better than any deterministic focusing. The other benefit of ensemble focusing is that the storm, for example, each storm may have a different predictability limit. And for some kind of storm on the ensemble space, it may reveal itself as giving pretty good merge in the spaghetti plot, so which is quite easy to predict using the model. But sometimes some other storm shows very diverse trajectory of spaghetti plot, especially for the trough. Then you can say this storm is not predictable using this model. Then, okay, in the sense of doing some kind of intervention, then this kind of storm is very hard to do some kind of effort in intervening at some stage to reduce down the storm intensity. So in that sense, my suggestion is that we first need to do some kind of clustering analysis out of long-term storm data. Then we can have a few clusters. One of the clusters may revealed that all these kind of storms are in the category of hard to predict in short range. Or some other cluster storms, they may reveal that, okay, these storms are quite predictable, or even for several days. So that kind of clustering, after the clustering, we can have some idea on which kind of storms we may deal with kind of easy intervention project. For others, we may need to have a much longer lead time to do something to control it here. So we need to make that kind of decision. To make that kind of decision, we need to have this kind of data set for different storm categories, which one would be, based on the characteristics of the storms. Then probably we may have a better idea on attack these kind of things.
Yeah, thank you very much. And also MIYOSHI-san said maybe we cannot control everything, but we can control some under specific conditions, maybe. And for tropical cyclone, maybe the mature stage, maybe it's really difficult, maybe no control at all. But maybe early stage, cyclogenous stage, and also weakening or decaying stage, maybe there is a hope. But we are not sure at this moment, but that's my feeling. And so that's why currently maybe for typhoon intervention simulation case, maybe including mature stage typhoon as well, right? FUDEYASU-san. So maybe you may think about the other stages as well.
Yeah, so we recently started the intervention at the typhoon at the genesis stage, but previously our focus, our effort were focused on the disaster prevention. So that's typhoon was approaching to Japan at that time. So as you say, the typhoon has a peak. Typhoon intensity has a peak. So as you said, it's very hard to change the structure and the intensity. But now we started to intervene with the typhoon at the genesis stage.
Okay, thank you. Maybe mainly we are talking about for typhoon, but also we have to include the heavy precipitation event as well. And as MIYOSHI-san said, we have some success to control the heavy precipitation events in the numerical simulations. And but we still have another 2 years to improve and also show the operability as well. So we have to show the result as well. So then, is there any further directions or improvement in simulating heavy precipitation event and also controlling these events? YOROZU-san or YOROZU-san?
Okay, thank you. Regarding the isolated heavy rainfall event, actually the important point is where we set the wind turbine. The location is very, very important. So we already conducted some of the sensitivity analysis. The wind turbine, the location is changing from here to here or from here to here, or the height is changing or size is changing. And we can find, finally we can find the best location of the wind turbine and also the size. But that can be found in the simulation. So I mean, the question is can we get such information in advance 2 hours, or 3 hours, or more, the 6 hours before? That is quite important. So probably that is the caused by the uncertainty of the weather forecast accuracy. But I think the uncertainty will remain in more in the future, I guess. Sorry for meteorologist. Actually, I mean the hydrologist. But anyway, probably the uncertainty of the model can remain even if the model is updating and updating. But what is important is we need to validate the impact of uncertainty itself. So even if there is uncertainty, for example, the location is different, but even if around here, we set the wind turbine, the rain intensity may not change, but the peak time is delayed from this the original time. In that case, that is quite helpful for people evacuate. So that kind of the information is very important. So I think the evaluation, how can I say, the way of thinking of the evaluation is changing in our mind. So yeah, uncertainty exists, but that's okay. Including the uncertainty, even if there is the uncertainty, we can get the benefit for the disaster prevention. Not only in the intensity, but the evacuation time or other the criteria. So that's I think important things. And in our team that we can discuss together with meteorologists and the hydrologists and the urban planning people, so that we can get such kind of outcomes. Okay, thank you.
Okay, thank you very much. Yasunaga-san, do you have a few words?
Yeah, in terms of the organized conviction, so unfortunately we don't have enough knowledge about the process of the organization. So we don't have enough knowledge about why convection is aligned in a line shape and how it is organized. So to reduce the uncertainty, so we have to make a progress our knowledge about the organization process of the precipitation system in the rainy season in Japan.
Okay. Maybe Kosuki project has a little bit short in the program, so that's why maybe you need more experiment in the numerical simulations as well, right?
Yes, yeah, we are conducting a lot of numerical simulations, and we also starting to discuss the field campaign for in the near future. So we have to discuss it because so we have to alleviate the social concern about the intervention processes. So we have to convince the society. So from that perspective, so we have to establish the very, acceptable field campaign, acceptable to the society.
I see.
So that is another point of our activity.
Okay, thank you very much. So then maybe in the same line, we would like to continue to discuss about the engineering devices, because we have to implement how to intervene. So actually lots of method planned so far in individual core project, but maybe in the simulations we idealized the setting, and maybe a little bit or completely different from the real instrumentations, I wonder. So at this moment, maybe no one not sure how to implement the engineering devices to control the heavy precipitation or typhoon events, but maybe one of the promising one may be cloud seeding by aircraft. But other methods like wind turbine is maybe mainly fixed locations, not movable locations. So that's why maybe the application is a little bit limited, I wonder. But still, if wind turbine is in the right place, right time for the occurrence of heavy precipitations, maybe it may work, but not always. So another 2 years we have to develop or work harder to do it. But is there any suggestion or direction you are thinking about? I would like to hear. Maybe a little bit tough question. Okay, Sawada-san.
Yeah, it is always really tough, but specifically for the tropical cyclone, I think that for now, maybe kind of one-shot innovation may not work. So, yeah.
You mean continuous?
Yeah, so we have to intervene continuously to the tropical cyclone, because tropical cyclone has a long life cycle, and also we have so many uncertainties. So maybe one shot, the intervention may fail, but we need to try again and again toward, yeah. But that's actually the good news, because we have many chances to intervene. That's quite different from the isolated convective cells or other many short life cycle events. So if your target is isolated convective cell, if you fail once, that's the end. But if in a tropical cyclone, you have many chances. But over the ocean, and we create a strong wind environment, and we need to intervene the tropical cyclone again and again by monitoring it. That's engineering. From the engineering perspective, it is very difficult. So someone including my team, someone tried to put the ship or to try to go to the aircraft, but there's so many aircraft, so many cloud seeding transferred from the land to the ocean. So that's kind of engineering. If you look at from the engineering perspective, it's quite difficult and costly. So yeah, we need to have many more breakthrough innovations to, of course, mathematically or meteorologically, we can improve the efficiency of each one of the interventions, but still, I think we need to continuously intervene the meteorological phenomena. So, yeah, so I do not propose any solution right now, but I can say that it is the most important difficulties that we are now facing with. And also, it might be related to the LC program, because we need to intervene again and again. Is that allowed by the general public? That's also quite an important issue. I thank you.
Okay, thank you. I fully agree with you, but what kind of engineering device we use by using a minimal effort, not so big energy. So that's most important part.
So the easiest idea to come up with is just using a drone, so many drones, or including, drone-like aircraft, ships, but still, it's going to be tough, right? So I don't know. I'm not, yeah.
Okay, any other suggestions and comments? No? Any suggestions from audience? Yes. Go ahead.
So, with our bushfire research, we're a little more advanced on the device side, and we made the decision early on to intervene very, very early while it was possible to intervene. The trick is there, how can you find, in the big, huge bushland, it's like a big, huge ocean, how can you find one tiny little fire? And so we thought, well, we first thought maybe a satellite, and we thought of all different, and then we thought we need all of them, because if one fails, you have another one, and if that one fails, you have another one. So you need to have the ideal layering, we called it a wedding cake layer, of different approaches to actually make sure you achieve your goal. The other issue that's different with the bushfires is it's ideal to be able to intervene very early with cyclones because it's much smaller and much weaker. But you have much more uncertainty about its track and its intensity, so when to intervene. So I just wanted to mention that as well.
Okay, thank you very much. Yeah, any comments? Yeah, Sarah-san?
Yeah, I was just wanting to comment on, as I'm listening to this discussion and putting it into my context of the weather modification work that we do, we have, ground-based generators that are those fixed assets that you have to put them in the right place because that's where they're going to be for the winter. But the good news is orographic clouds kind of give us that fixed location. Then there's the aircraft opportunity, but a lot of these aircraft have pretty limited on-station time, especially when you're flying them in very challenging icing environments. And, as you just mentioned, this idea that you need to get out over the ocean then, so you have that transit time from land to wherever the cyclone is, that is a challenge. With drones, that's an up-and-coming way that some organizations are looking to do cloud seeding. Of course, the drones have to be able to also withstand icing, but they're not going to have much of a transit time at all, but a combination perhaps of an aircraft that can release a fleet of drones out over the ocean. Whether or not you want to recover the drones, or if you can recover the drones later, will be another question on how cheap you can make them and stuff. But that combination approach, I think, is where it might be more feasible. But yeah, the battery power, all of this stuff for drones, it's increasing every day, so it will be interesting to see where that technology goes.
Some institution already developing the drone operations?
Yeah, there are some companies that are looking at developing drones for cloud seeding, but again, the big challenges are payload, shrinking and minimizing the weight in order to give more on-station time. In the US, we're not allowed by our aviation administration to fly a drone out of line of sight, so that also limits right now where they can be flown. You can't fly them in the cloud where you want them. And then if you are ever able to get them in the cloud, they would have to withstand icing, which will also take more power from the battery, but also need specialized equipment. So there's still some challenges, but I think they're all something that can be overcome.
Okay, thank you. You have some further comment?
Just on the drones, so we have struggled with this for the bushfires as well, because the drones, we've found some that can fly 100 kilometers and they're quite fast and everything, but what you really need, because you need so many of them and they're going to have so many payloads. So we have this genius engineer in our team, and he came up with these, what we've called water gliders. So they're like disposable, like a bomb, like a big bomb made out of the disposable material. He thinks maybe you could even make them out of very strong cardboard. You may have to have a lining of some sort. And you would have 40 of them in a very large aeroplane, and you would drop them like you drop parachutists or bombs or something. And then they have a small, very cheap autopilot on them. He's the world experts in autopilots for drones, and they have a very cheap autopilot on them, and you can direct them to exactly where you want them to go. And then in the case of a bushfire, just before they get there, a parachute opens, so they don't do the wrong thing, but you probably wouldn't necessarily need the parachute. Maybe, I don't know. I have to think about that. But anyway, when my director saw the work we're doing in the bushfires, he said, this would be great for cyclones. We could use these. And I think it's really worth considering because if they get developed, we haven't built full-scale ones. They're supposed to hold a half a ton of water once they're full-scale. We've only built small ones, but they could be really successful interventions, I think, in this case. So.
Okay, thank you. And we only have 5 minutes left. So maybe I will ask the final question to you. maybe one of the most tough questions. Do you believe that we can control the high impact weather by 2050? Who answer first? Maybe my assumption is everyone say yes, right? Or any objections? Maybe some under conditions, right? I suppose. Sawada sensei?
Yeah, I'm quite optimistic, but yeah, of course we need have some the breakthroughs that we have already discussed in this panel discussion from the both scientific perspective and engineering perspective. So specifically the model uncertainties or new theories or new understanding of meteorology and the engineering method to continuously intervene the phenomena. But yeah, I'm quite optimistic. Thank you.
Yeah, you can contribute, right?
Of course I do. Of course I do. I'm so optimistic so that I'm joining this project. So yeah.
Yeah,
of course
thank you very much.
I have the obligation to do that.
Yeah. Who's next?
Yeah, so.
Oh, okay.
Maybe.
Sensei, please.
Okay. Yeah, so I think, yeah, I believe so. Scientifically, yes, but so even, for example, typhoon control becomes possible scientifically. So LC problem, LC is very hard. So, but so now, so we are researching on the typhoon control, but all of my group, some of my group doesn't want to typhoon control. So we are very thinking about how to intervene with the typhoon to reduce the typhoon intensity. But so different opinion. So I mean, so scientifically yes, but LC is hard.
Okay.
Okay, can I?
Yeah.
Okay,
please.
so first of all, I'd like to answer my personal opinion. I believe yes. So, but this July there are some workshop, and I and several colleagues, of course, including the project manager, Professor Yamaguchi, and except the Professor Yamaguchi, we can say yes. But his answered, how can I say, partially no, because he understands there are several steps we need to solve. But he said, yeah, actually now we need to solve this thing, many things he already understands. But finally he said, but he believes he not only him, but including all the project can solve all the things, and then we can achieve the goal. So probably the participants can say yes, probably thinking the optimistically, how can I say it? But the project manager, like them, understand the difficulties, so it is not so easy to say yes. But for the participant, I guess or some of you think yes that we can do. So that's my answer. Thank you.
Okay, thank you very much.
Okay, so my answer is also yes, of course, but I'm sure Kotsuki-san's answer, but my answer is yes. So actually, so for now, we have two options to control the weather modification. So one is a kite or wind turbine-like object to disturb the flow of the air. And the other option is cloud seeding. But we have to look for other options to more efficiently control the weather. So in 2 years, we have to look for another options to control especially the organized precipitation which occurred in the rainy season in Japan.
Okay, thank you. So all four PM said yes. Very strong support, and then maybe Miyoshi-san say a few words to summarize.
Okay. So if I go out and look at the sky, I can see clouds, maybe single cloud, yes. But I cannot see tropical cyclone as a whole because it's like several hundred kilometers scale and the visibility is much less. So we need to go to the space to see the whole clouds of forming the tropical cyclones. So there are two PMs, SAWADA-san and FUDEYASU-san. Believe yes? Show me the results, please.
Next year.
So that I can say yes here. That's my comment.
Okay, thank you very much. This is the end of panel discussions. Thank you for all panelists. Yeah.